So the problems that you looked at for bonus on the derivative investigation, they were good examples of the chain rule, as they had a new look to them. They had an inside and an outside function. Now, let me show you another example that you can kind of start your notes with of a function that has a perfect inside and outside. So we have here y equals the sine of x squared minus 4. And we're trying to help you see that there's two functions, but one of them is on the outside, and that would be the sine function. And then there's a function on the inside. And on the inside, we see x squared minus 4. So that means that the derivative is going to require us to follow this thing called the chain rule, where you do the derivative of the outside. So the derivative of sine is cosine. Now, the part that is kind of the hardest for students, but it's actually really easy to do, is just leaving the inside alone. So what we see here is x squared minus 4 unchanged. And this is part of the chain rule. So we have the derivative of the outside, which is cosine, with the inside left alone, which is x squared minus 4. And now we're going to chain, or we're going to multiply to the end of this answer, the derivative of the inside. And of course, the derivative of the inside would be 2x. The chain rule. Doing the derivative of the outside, leaving the inside alone, and then doing the derivative of the inside. A lot of times we'll rewrite the answer so that the power function, in this case the 2x, is in front of our trig function. It just looks a little more proper. Let me show you the chain rule with notation. It's actually kind of the formula for the chain rule. Now, first thing you got to understand is that the types of functions we're going to be dealing with are functions that are compositions. A composition is when we have a function within a function, or as we keep saying, a function on the outside and a function on the inside. So we have f of g of x. Now, to do the derivative, I would have to do the derivative of the outside, which would be f prime. Leave the inside alone, which would be g of x, and then the ever-famous derivative of the inside, which would be g prime of x. This is the notation. You actually will use this notation for a challenging problem that we'll do at the end of this lesson. It turns out that most students, when they think about the chain rule, will think about it with the language that you've heard me say a few times. And what I'd like to do now is work through a couple examples where we can follow this chain rule, where we do the derivative of the outside, leave the inside alone, and then we'll do the derivative of the inside. All right. The other thing that's important is just to realize that the types of problems that we're looking at now, they're different. They're different. And they're different because they have multiple functions. They have, in this case, two functions. And the first thing we want students to be able to start to see is in a problem like this that I have y equals 4x squared plus 2, the quantity squared. So we've got 4x squared plus 2, the quantity squared, that the square is actually our outside function. And a lot of times it's easy to say that because the inside function is going to be the one that's in the parentheses. So the 4x squared plus 2 is on the inside. All right, so time for the chain rule. Derivative of the outside. Now when I do the derivative of the outside, I'm going to be using the power rule. So I get 2, the quantity, to the first power. I just want you to see that that's the derivative of the outside. I bring down the 2. I have this quantity, but it's now to the first power. Okay. Of course, you do need to leave the inside alone, so we'll put down 4x squared plus 2. And then you're going to multiply, you're going to chain onto the end of this, the derivative of the inside. So the derivative of 4x squared is just 8x, and the derivative of 2 is 0. We end up with 8x. 2 and 8x are coefficients, so you need to multiply them together. You get 16x. Then our 4x squared plus 2 we can put beside it. Now that answer is totally fine. However, because we're going to end up doing this problem another way in just a moment, let's distribute. Let's distribute so that you can see the answer in more of a polynomial form. 16x times 4x squared is 64, x to the third, and then 16x times 2 is 32x. And that answer is also fine if you would want to do that. The real reason I did that is because I want to show you an alternative method. Now, an alternative method is going to have us use algebra as our first step, and then we'll end up using calculus as our second step. So since I had 4x squared plus 2, the quantity squared, I could actually do the FOIL method. I could do the FOIL method first. And if I did the FOIL method, I would end up with, well, 16x squared. Let's just kind of separate this. 16x squared plus 16x. Hold on a second here. It's 16x to the fourth. So we get 16x to the fourth plus 16x squared plus 4. Now, I did the FOIL method. I kind of did a little bit of the thinking in my head, but remember, that's just some good algebra. Now, if that's your y equals, then what would be your dy dx equals? Well, now we're going to do calculus. Interesting. If you do the derivative, that would just be bringing down or doing the power rule. So I guess if I bring down a 4 times 16, 4 times 16, oh, that's 64. Subtract from the exponent, and I get x cubed. Look, if I do the power rule here, I'll bring down this 2. That'll give me 32. Of course, 32x as your full derivative. And if you look at the derivative of your constant, of course, that's 0. Now, I'm not trying to say that we don't need the chain rule. What I am trying to say is that the chain rule that I'm showing you works. The chain rule is legitimate. Okay, because we were able to do this problem with an old rule, it proves that this new rule is also fine. Okay, most of today's lesson is understanding that we need the chain rule. And so let me do a problem with you that we need the chain rule. It also has a square root in it. It's y equals the square root of 24x to the fourth minus 7. We'll talk about why a square root sneaks into this lesson. Okay, and for the simple reason that a square root is the same as an exponent. So remember from algebra class that a 1/2 power is the same as a root, as a square root. Well, another perfect example of the chain rule. And the reason it's a perfect example is because we have an outside function and we have an inside function. Okay, when you see two functions, one on the outside and one on the inside, we're going to be using the chain rule. Now use it carefully. You do the derivative of the outside. And when you do the derivative of the outside, you have to bring down the 1/2, but you also have to subtract and get negative 1/2. Okay, that's the derivative of the outside. Of course, the inside left alone is just recopying 2x to the fourth minus 7. And then you have to chain onto this. You have to chain the derivative of the inside. And the derivative of the inside is just 8x cubed. A square root problem is really a chain rule. Now, it turns out that 1/2 and 8 can be multiplied together. That, of course, will give us 4. The x cubed can come along with that. It also turns out that the negative exponent is a no-no. So instead of writing it with a negative exponent, we're going to bring that down to the bottom and write it as a positive 1/2. Okay, inside functions, outside functions. Now, just like I did in the little intro problem, trig functions are also good functions for chain rule. So how about 3 times the sine of 4 over x squared? Okay, when we have a trig function, there's a good chance that it's going to be a chain rule. Okay, now the reason it's a good chance is because whenever you have something in parentheses, that's our inside. And then that makes the trig function the one that's on the outside. So when you do the derivative, now I'll tell you what, this 3, I put this here as a coefficient so we could just mention one more time that coefficients always come along. So 3 just comes down, not really part of the derivative, it's just that it needs to, I shouldn't say it's not part of the derivative, we just don't change it as part of the derivative rule, it just comes along. All right, derivative of the outside, derivative of sine, cosine. Leave the inside alone. I'm telling you, that's the part that people forget. They want to do the derivative of the inside too soon. Speaking of the derivative of the inside, this is a good opportunity for us to put one of these little thinker bubbles down, because remember how you have to think of 4 over x squared? You have to think of it as 4x to the negative 2. We always think of that as a negative exponent. So that you can chain on the derivative of 4x to the negative 2. The derivative of 4x to the negative 2, remember, is negative 8x to the negative 3, because we have to subtract from that exponent. But then since we get a negative exponent, we're going to want to flip that down to the bottom. And I didn't give myself quite enough space here, but I end up with this negative 8 over x cubed. And that, of course, is being chained or multiplied onto this answer. Now, 3 that copied down and negative 8 that is part of my derivative, we should multiply those together to be negative 24 over x cubed is coming along. And then I have my cosine of 4 over x squared. Okay, so trig functions often use the chain rule.